Welcome to Engineering Mechanics Dynamics, and this is a part 2 on a lesson of rectilinear kinematics, and we're going to start off with acceleration as a function of position. And here's the first idea we're going to talk about, and that is acceleration equals the instantaneous change in velocity with respect to time, which ends up becoming velocity times the instantaneous change of velocity with respect to position. And I will show how you can get from there to there. And so V equals ds dt. So you rearrange that and you end up with dt equals ds over V. And then A equals dv dt. And then if you plug this into there, you end up with A equals V, you're multiplying by the reciprocal, dV over ds, which is what you have right over here. And then we have becomes this, and so if you rearrange that equation or this equation, you get V dV equals AdS, which becomes that integral. Now we're going to do an example. A particle travels along a straight line with an acceleration of 10 minus 0.2 s meters per second squared, where s is measured in meters. Determine the velocity of a particle when s equals 10 meters if v equals 5 meters per second at s equals 0. So given we have acceleration as a function of position and velocity at a position, and find v when the position equals 10 meters. And so to solve this, we're going to use our acceleration as a function of position idea. And so v dv equals acceleration ds. So we put that in, and we go from 5 meters per second to final velocity of v dv equals, going from position 2 to final position s, of 10 minus 0.2 s ds. And so if you solve out that integral, I'm not going to do that for you, you can do that in your own time. V ends up equaling the square root of 20 times s minus 0.2 times s squared plus 25. And then if you plug in s equals 10, so at s equals 10, v equals 14.3 meters per second. And that is how it is solved. And now we're going to go over acceleration as a function of velocity, and there are two ideas to help you solve this. Here's the first, and so it's just rearranging your acceleration equals the instantaneous change of velocity with respect to time to make it just like this. And so then you can take the integral on one side and the integral on the other side. And the other is right here. And so this is very similar to having a sub s d sub s equals v d sub v. But now we just bring this term over and put it under because it's now a sub v. And you end up with that. And now we're going to do another example problem. So initially a car travels along a straight road with a speed of 35 meters per second. If the brakes are applied and the speed of the car is reduced to 10 meters per second in 15 seconds, determine the constant of deceleration of the car. And so our initial velocity is 35 meters per second, and our velocity equals 10 meters per second at 15 seconds. Find constants of acceleration. And so first off, when you look at this problem, you need to understand that its acceleration is a function of velocity, because because we're giving velocity and times. And so then it can either be one of these two equations, and since we're not giving a change in position, we're giving a change in velocity and a change in time, then we're going to want to use this equation. So then this becomes from 0 to 15, d sub t equals from 35 meters per second to 10 meters per second of d sub v over k. That's our constant. And then you solve both of those, and you will end up getting 15 equals negative 25 over k. And so then k equals negative 1.67. And that is our answer. So it's decelerating at negative 1.67 meters per second squared. I should have had units throughout all of this. Hopefully this lesson helped you. And good luck continuing to learn dynamics. If you have any questions, never be afraid to ask. Thanks.